Hello and welcome to PC Retro Tech. So today is the second in our series on this Cga graphics demo, and I'm going to be showing you how to do some programming with the Cga adapter. In particular, I'm going to show you how to draw dots on the screen and how to do a Starfield demo. I'll also be talking a little bit about drawing a bounding box and how to clip objects. So here we're clipping all of the points that are being drawn into a small square in the middle of the screen, and I'm going to explain why you might want to do that and show how it's done in this case. So here's the Starfield demo. You can have a look at the longer video on this entire Cga demo if you want to, but this is what we're going to be coding up today. So this is basically just a set of points on the screen. They're either blue or white. They start off blue and they become white as they get closer, and they have the appearance of moving towards you like you're flying through space. So we're going to go through all the basic elements of how to do this, starting with how the Cga adapter works and how you program it. So I'm showing the demo today on this 286 PC. This is a little bit more recent than the Amstrad PC 1512 that the main video on this demo is shown on, and the reason I'm using this is because it's just a little bit easier to develop on this machine. It's a little faster, in fact 3 or 4 times faster, and I also don't want to have a lot of wear and tear on the older machine. Of course, this is also a rare machine in its own right, and I'll feature this on the channel at some later point. Another reason to use this machine is that the graphics itself are much easier to film. This is an LCD monitor which has a much better interplay with the refresh rate on my camera. So this particular machine has a VGA adapter in it. In fact, it's a Sanglabs ET3000AX. It's a 16-bit ISA card. But all EGA and VGA adapters had the ability to emulate the Cga adapter, and you program it in exactly the same way, so precisely the same code that works on a genuine Cga adapter will work on this VGA card. Of course, there's another way you can do this, and you can do this is on a modern machine, and that is to install DOSBox, and DOSBox will give you an emulated Cga adapter if you ask for it. So I'm not actually going to show you the code on this particular machine because filming the screen like this is not going to be very clear. Instead, what I'm going to do is bring up a screencasting tool on a modern laptop. That'll enable us to use a modern editor with syntax highlighting and so on, and move around the code much more easily than we could do on this old 286. So the first thing I want to do is show you how I've got this machine set up. I've got it set up so it's easy to do both assembly language and C, and you can see from my directory structure here I've got one directory called TC, and that's where the Borland Turbo C program is residing, and a little bit further down, about halfway down, there's TASM, which is the turbo assembler also from Borland, and this allows us to do assembly language. So that just needs to be installed on the machine, and the same with the C compiler. The code itself is in a directory called drawing. So here are the C files in that directory. I have a number of different files here. Drawing is just a very early version of some code. There's some code there for drawing lines on the screen, ellipses. The Cga demo, which is the code for the demo that we're going to be looking at today, which of course does many other things. And then there's line R1, which is just the most recent code that I've been working on, which allows you to write lines to an array instead of to the screen so that they can be used for other purposes. And I'll discuss that in a later video. So for now we're going to be concentrating on Cga demo. The other part of this is the assembly code, and this is in a file called cga.asm. So this is pretty long by now, but it has all the routines for drawing dots, drawing lines, drawing ellipses and so on in assembly language, and these are used by the Cga demo to draw all the various effects that we have. So a lot of the control code tells the machine exactly what to put where. is in C, and the ones that actually draw the primitives, the graphics primitives, are done in assembly language because we want those to go as fast as possible. So the other thing that's really important here is to set your machine up so that your keyboard is using the correct code. In this case I've got a UK keyboard, so I'm calling the DOS keyb.com, which is set to UK keyboards, which is what I have here. I've installed a mouse. That's so that I can use a mouse within this editor, although I have to admit I tend to use the keyboard for most of my editing, even for copy and paste. And the most important part of all is this set path command. So this sets the path to all of the applications that I want to be able to run, so that I don't have to actually be in the TC directory or the TASM directory and so on in order to run the commands. So of course DOS is there, $DOS, and there's also a paintbrush tool which we'll investigate a little bit later. That's for drawing shapes and doing graphics on the machine. So if we want to write a demo or a game or something that has complicated graphics, we can draw them in that. Then of course there's TASM and TC, so that's the assembler and the compiler, the C compiler, and the editor itself. So I'll talk a little bit about the editor in a moment. It's the editor that you see on the screen here. It's called the Cedar Island editor, and I found it to be generally pretty good. So it does support the mouse, it has pretty easy to use copy and paste, and you can search in the file. It has all the basic things that you would want to have in an editor. Of course, if you want to do development on a modern IDE, you can do that as well, but then you've got the problem of shuffling the files across on floppy disks onto the machine. So before I get started, let me just mention that all the source code for this demo is available online on GitHub, and there's a link in the description below, and you can download that and use it for any purpose you like. The first file that I want to have a look at is makefile, which is this file here, and it's basically a set of instructions on how to build Cga Demo.exe from the two source files Cga Demo.c and Cga .asm, which are the C and assembly files respectively. So make files are very convenient because instead of having to type TASM blah 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 and TCC blah 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 every time you want to build the project, you just type make at the command line. Make looks for a file called makefile, and inside it is a set of instructions that it follows to build the executable. So there's two steps here. The first step is to build an object file from the assembly file. So this is basically just assembling the .asm file, and this is done using TASM, as you see in that second set of instructions there. And the second step is to build Cga Demo.exe, which is the first set of instructions here, and for that you need the C file and of course the object file that we just built. And this is done using TCC, the Turbo C compiler, and this is the set of commands that you'd have to type every time if you wanted to build it. I've also given some optimization options here, this -G, O and Z, so that the final executable will run as fast as possible. So I'm going to start with this file Cga Demo.c, and I'm using Visual Studio Code here, which is a convenient editor to use on Microsoft Windows. And the file starts off with inclusion of various headers that are required. So there's ones here for printing to the screen, allocating memory, keyboard input, various DOS stuff including interrupts which we'll need to control the Cga adapter, and random functions in time.h. So the code itself starts off with declaring a bunch of functions which are defined somewhere else. And so they're extern. In this particular case they're in assembly language, and we're going to focus today just mainly on this first one, Cga draw pixel, and possibly the next two here, set y and draw pixel x, which is an alternative way of drawing pixels to the screen. If we scroll down, we see there's a lot of C functions for various things like lines and ellipses, and it goes on for quite a while, getting progressively more complex. The actual code that we're going to look at today starts here. This is the main function, which is where execution starts. And I'm going to assume that you know a little bit about how to program in C and assembly language for this demonstration. If you don't, you can just follow along, and this will be an introduction to what this sort of stuff looks like. So the first thing we do is we set up the random generator. Then we set the video mode to 4, which is the Cga 320 by 200 4 color mode. Then we wait for a key press, in particular the enter key. And this is the code that we're going to look at first. So this is the part that just draws random pixels on the screen. It's a loop. It waits until a key is pressed, and then it gets that key out of the buffer so it doesn't interfere with any later part of the program. So it basically just draws 5,000 random pixels to the screen using this function, Cga draw pixel, which is in assembly language. It's going to have coordinates between 0 and 320, not including 320, and 0 and 200, and it's going to call this function with the color J. So J starts out as 1, the color 1, and it increments the color each time by setting J to J plus 1 each time, unless J is 3, in which case it goes back to the color 1. So these are the three non-black colors, cyan, magenta, and white. After each 5,000 pixels, there's a delay. It blanks the screen, which is another function I've written actually in C in this case, and it loops again and draws the same thing, 5,000 pixels, but in the next color, and so on. So let's start with this set video mode function. So it takes a single parameter n, which is the video mode we want to set, in this case video mode 4. And it's a very simple function. It just sets some registers and then calls an interrupt. In this case, interrupt 10H, 10 hexadecimal, which is the BIOS interrupt for controlling the video adapter. The first thing we need to do is set two parameters. So the first parameter goes in the AH register, and that is the function that we want to call. In this case 0, which corresponds to set video mode. The second is setting the AL register, which is where we need to put the actual video mode itself. So in this case we would have n equals 4, so it would set AL to 4. And then we call the interrupt itself, and that will go off and set the Cga adapter to mode 4, and that's the 320 by 200 mode with 4 colors. So before we have a look at the code for actually drawing a pixel on the screen, we have to explain a little bit about how the Cga adapter works. So it's basically controlled by a bunch of registers, which we won't need to touch for this demo. And in order to actually draw points on the screen or dots on the screen, you simply write into the memory of the Cga adapter. So that starts on any of these machines at address B8000, so it's a hexadecimal address. Now the first thing you might notice about this address is that it's more than 4 hexadecimal digits long. It's actually 5 hexadecimal digits, and we're working on a 16-bit machine which has a limit of 4 hexadecimal digits for each pointer. So how do we actually address this? So the way this is done is using a segment and an offset. So we break this address up into two parts. The first is just B800, which does fit in a 16-bit register, and the second is an offset 0000. And the way it computes the address from these is it shifts this segment address left by 4 bits, and then it adds the offset. So that has the effect of giving us 5 hexadecimal digits for the address. And in this way, the machines were capable of addressing up to a megabyte of memory. So how is the screen memory laid out? Well, it's starting at offset 0000 is line 0 on the screen. So this is the first horizontal line on the screen. And then weirdly enough, they made the decision to draw only the even lines in the first part of the screen memory. So at offset 0050, which is 80 in decimal, they have line 2, and then so on. Then at offset 2000, which is actually 8 kilobytes into the screen memory, they have the odd lines. So this is the first odd line on the screen, or actually the second line, and this is the second odd line, and so on. So each line is 80 bytes long, and if you're very quick with the math, you might realize that 80 times 100, there'd be 100 even lines here, is only 8,000 bytes. It's not quite 8 kilobytes, which would be 8,192 bytes. So there is actually a little bit of extra space that's not used at the end of the even lines, and similarly at the end of the odd lines. There's a few extra bytes which you can store information into. It's real memory, but it's not displayed on the screen. So each byte has 4 2-bit fields. So each of those 2-bit fields can contain 00, 01, 10, 11. So these are the colors: 0 for black, 1, 2, and 3. So they're the 4 colors that can be displayed. And so each byte has 4 pixels stored into it, each in one of these 2-bit fields. So let's discuss how the draw pixel command works. This is in the file cga.asm. So we have to start with 3 assembler directives to tell the assembler how to handle this code. In particular, we tell it that everything from here on is actually code, and that we're going to use a small memory model. So I won't go into the details of the memory models. You can look that up online, but this is just required to get things started. So here's the actual CGA draw pixel function. It takes 3 arguments, x, y, and color. So these are the x and y coordinates and the color. These are integers in C, so that corresponds to 16-bit words, and the color is just a byte, so that's an 8-bit byte. Of course, it can only take 4 values. Now notice that the CGA draw pixel function has an extra underscore in the name here, and that's because the C compiler adds an extra underscore to all the function names behind the scenes. So we have to match that in assembly language. So the first thing that we do in this function is we set up the base pointer, the BP register, to the current address of the stack pointer. So these parameters will have been passed on the processor stack. And so by doing this, we enable this notation to access the parameters that are passed in. So if I want to move the Y coordinate into the AX register from the stack, this BP, setting BP to SP, enables this notation to work. And here's the X coordinate and the color. So the first thing we have to do is set the segment register to the B800 hexadecimal address. So for this, we're going to use the E segment register. We can't put the value straight in there. We have to go via the AX register. That's just a limitation in assembly language. And the next thing that we're going to want to do is compute the offset of the pixel in the screen memory. So there's 2 parts to that. The first part, we have to compute the offset of the line, and the second part, the pixel within that line. And right at the end here we have the function that will actually move the pixel information onto the screen and actually draw the pixel. So the first thing that we have to do is compute the offset of the line. Now remember, each line is 80 bytes, but we first need to take care of whether it's an odd line or an even line. So the last bit of the y value is going to tell us whether it's odd or even. So what we do is we shift right this value by 1 bit, and that puts that 1 bit into the carry flag. So what we can do here is a little trick. So we set the DI register to 0, and then we subtract the carry, which is this SBB instruction, from DI, and this will either set DI to all zeros if the carry was 0, or it will set it to all ones if the carry was a 1. So in other words, if we had an odd line, we'll now have all ones in the DI register, otherwise we'll have all zeros. Now we can AND that value with the value 2000. Now remember, 2000 was the address where all of the odd lines start in memory. So in other words, if the carry flag was a 1, we'll now have the value 2000 in the DI register, otherwise we'll have 0, which would be the offset of the even lines. So now the DI register has the right offset for either odd lines or even lines, and all we need to do is multiply the line number by 80, and we'll get the actual offset of the line, and we'll add that to the DI register at the end here. So of course I don't really want to actually use a multiplication instruction here because that's very expensive on these processors. So instead of doing that, I use a bunch of shifts. So I do 4 shifts to the left by 1 bit, and that's equivalent to multiplying by 16. And then I save that value, and then I multiply again by another factor of 4. So 4 times 16 is 64. And I add that value. So 16 times a value plus 64 times a value is 80 times the value. And this sequence of instructions, although it's very long, will be much faster than doing a single multiply instruction, which could take 120 cycles or so. So I add that value to the DI register. So now I have not only whether or not it's an odd line or an even line, but I have the line number multiplied by 80. So now I compute the offset of the X pixel within that line. And so this is done using this sequence of commands. So remember that each byte contains 4 pixels. So I want to divide the X coordinate by 4, and that's done by shifting right twice by 1 bit, which has the effect of dividing by 4, and of course that's way faster than a division instruction, which is even more expensive than a multiply. And I add that value to the DI register. Before I did that, I saved the X pixel information into the CL register so that I can manipulate it a little bit further. So the first thing I want to do is increment the value. So it's going to be in the range 0 to 3. So after incrementing it, it'll be in the range 1 to 4. And of course there could be other information in here. I've just taken this from the offset of the X pixel. I'm only interested in the 2 bits that correspond to the whether it's pixel 0, 1, 2 or 3, and so I have to AND the value with 1 hexadecimal, which is 3 in decimal, and that'll give me just the last 2 bits, which correspond to whether it's pixel 0, 1, 2 or 3 in the byte. I then have to multiply that value by 2 because each pixel takes up
2 bits, and I'm then going to take the color, which was passed in by the stack, and I'm going to rotate that color right by the number of bits that I just computed. So if it was pixel 0, this would do no rotation. If it was pixel 1, it would rotate by 2 bits, and so on. But remember, we incremented that number by 1 and then multiplied by 2. So in fact, if it's pixel 0, it will rotate by 2 bits. If it's pixel 1, it will rotate by 4 bits, and so on. And this has the effect of shifting the color information into the correct 2 bits within the byte DL. So of course I can't just write that byte onto the screen because that'll set 4 pixels. It's not going to just set the 2 that we just computed. And I don't want to mess up the other 3 pixels that are around that pixel that I'm interested in. So the first thing I have to do is compute a mask, and I have to take the existing pixel information and mask off the bits that I'm interested in. So the mask is done in exactly the same way as the color information, except that instead of putting color into the byte, I put in a value which is all ones except at the 2 pixels I'm interested in. So, and then I rotate it by exactly the same amount so that it lines up with the color information. So this mask is basically going to have all ones except for the 2 bits I'm interested in, which will be 0 bits. Then I'm going to AND that with the byte in the screen memory, the existing byte in the screen memory. So that'll have the effect of getting all of the bits except for the 2 that I'm interested in, because those are the bits I don't want to affect. So I don't want to affect the bits that I'm not interested in. So that's what this AND is for. And now I simply put in the extra 2 bits of information that I computed from the color, which have been shifted into the right place. And that's done with an OR, a logical OR. So now we have all of the original bits except the 2 bits we're interested in, and I've put in the extra 2 bits of information. So now this has all of the original pixel information on the screen updated with the 2 bits for the pixel I'm interested in. And the final command here is this stosb command. So this is the assembly instruction for taking the value in the AL register and putting it into the ESDI location. So you remember that we set the ES to be the B800 segment, and all of this code down here computed the DI offset for the pixel that we're interested in. So this combination ESDI here specifies the segment and offset of the byte that we're interested in, and the stosb instruction simply puts the AL value that we computed, that's with all the pixel information that we're interested in, into the ESDI location, and it also happens to increment DI, but that's not relevant here since we don't use it anymore. And we finish off by simply popping the DI register off the stack. We had to push that onto the stack at the beginning because this is one of the registers that the C compiler doesn't want us to modify. So we have to save its original value here at the beginning with a push instruction and pop it back off the stack at the end to restore it to its original value. And of course the other register that we changed is the BP, the base pointer, which we set so that we could access the parameters that were being passed on the stack. And so because we modified that, we also have to pop that back off the stack at the end before finally returning from this function. So this return will take the processor back to the original C code that called this CGA draw pixel function. So now we want to cover the actual Starfield demo itself. This is a function called Starfield, Cga Starfield, and basically it draws some random stars, 100 random stars on the screen, and it updates their coordinates so that they appear to be moving towards you. Now the way we do this is we create a C struct for each star, and this is the layout of the struct. So it has an X and Y coordinate. It has the old X and Y coordinates where the star just was previously to being updated, and we need this because we need to black that out before we write the star into the new location. And of course it also needs a Z coordinate. Now screens don't have Z coordinates, so somehow we're going to need to do a computation to figure out what the real X and Y coordinates are going to be based on this X, Y and Z coordinate here. So here's the Cga Starfield demo itself, and it's a function which starts off with a bunch of structs, those star structs that I just showed, in an array. So there'll be 100 of these structs, one for each star. And of course the first thing that we want to do is just create a bunch of random X, Y and Z values for those stars. So they'll be just distributed randomly throughout space. So we have a loop and it waits for a key to be pressed. And what this loop does is it loops through each of the stars, each of the 100 stars, and it does various things. So the first thing that we have to do is to black out the old star, and then the next thing we do is update the position of the star, so change its Z coordinate. In this case we just decrement the Z coordinate by 2, and then we have to draw the new star. And it could be that the star has finally run out of room, it's not on the screen anymore, and so we need to generate a new star to replace it. So that's the final part here. So let's go through all of this in a little bit more depth and see how it all actually works. So the first thing we do is, if we're not on the first star, so this is just a little flag that I set to work out whether this star has been drawn before or not. If we're not on the first star, then we get its coordinates X and Y, and this is for clipping. So if it's clipped, it calls draw pixel clipped. There's nothing else that we need to do here because the clipping will clip it to a point on the screen. If it's not, if we're not using a clipped box, then we want to clip the coordinates so that they're actually on the screen. It could be that the X and Y coordinates have been updated in such a way that they wouldn't actually be visible, and they're not in the range 0 to 320 for the X coordinate and 0 to 200 for the Y coordinate. But if it is in that range, then we call our assembly function. So this is the assembly code that we just went through for drawing the pixel on the screen with that old X coordinate, old Y coordinate, and the 0 color. So that'll black the pixel out. So this is only for stars that have already been drawn. If they've not already been drawn, then this won't run. So after we update the position of this current star, we check and see whether or not its Z coordinate is bigger than -100. This is just a value that I've picked. If it's less than this, it's probably not on the screen anymore, and so there's no need to draw it, and so we should generate a new star. So here's how the star should be drawn. So as I said, you can't just draw it at position X and Y because we have X, Y and Z coordinates. There's a little formula here for giving a kind of perspective for an x, y, and z coordinate, converting that to a real x and y coordinate. So in particular, the star coordinates are going to be centered around the center of the screen. So 160 and 100 are the coordinates for the center of the screen, because the coordinates could be positive or negative. And what we do is we take the x coordinate and the y coordinate, multiply them by 256, and then we divide by the z value shifted appropriately. So this is a very cheap way of giving a kind of perspective effect. So for computing a real x and y coordinate from a nominal 3D x, y, and z coordinate. And the reason why we're using this instead of something more complicated is because it just requires a single division. Remember that division on these processes is extremely expensive, so we want to minimize the number of multiplications and divisions that we're using. We could have actually done a shift left by 8 bits here, which would have been much more efficient than a multiplication by 256. And I have to admit that it's worth trying this out, because I'm not sure whether this compiler will actually recognize that multiplication by 256 can be done with a shift. So I haven't thought of that optimization before, and I'll give that a go a little bit later and see how it turns out. Again, if the pixel is going to be clipped into a clip box, we call the CGA draw pixel clipped, which, well, all it really does is just compare the coordinates with some clipped coordinates which are stored elsewhere, and if it's inside the clip box, it draws the pixel using CGA draw pixel. If not, it doesn't. So I won't cover that function because it's very straightforward. Here's the main one here. If the coordinates are on the screen, once again it draws them at position x and y, and of course it has to compute the color to use. So this is just a little formula which if the pixel has z coordinate less than 150, it's going to draw it in blue, otherwise it's going to draw it in white. Now, of course, if the pixel is not visible anymore because its z coordinate is too low, then we need to generate a new star, and instead of setting a random z position this time, we're always going to set the z coordinate to 256, which means that the star is far away. We don't want stars just appearing randomly out of nowhere in space. We always want them to be appearing in the distance. But otherwise, the x and y coordinates in the xyz space will be set randomly. And here is that first equals 0 flag. So this makes sure that when I draw a pixel for the first time, it's set to 1, but if I've just drawn a pixel, then first gets set to 0, and that means that it's going to need to blank out the old pixel before drawing the new pixel. So the CGA blank screen function is pretty straightforward. All it does is draw 200 horizontal lines, one for each y coordinate on the screen, and those horizontal lines stretch from the left hand to the right hand side of the screen, and they are all set to the color 0, so this is very straightforward. The CGA draw H-line function is actually in assembly language, so we'll take a look at that next. So now let's look at the code for the function CGA draw H-line, which draws a horizontal line on the screen. It's quite a general function. It can start at any x coordinate and end at any x coordinate, and of course you give it the y coordinate of the line you want to draw, and of course you can set the color to any one of the 4 colors. So first of all, we set up our segment register, and we set it up a little bit differently here. So we certainly set it up to be 800, but we add in the offset for the odd or even line. And This is okay because that offset is divisible by 16, so all we need to do is shift the offset right by 4 bits and add it to the segment register, and that'll have the same effect as putting the offset directly into the DI register. So now we need to worry about the bytes corresponding to the endpoints of the line. So there's going to be one of those for the pixel at coordinate x0 and one for the pixel at coordinate x1. So we set these up separately in different registers, and then we put the color information into another register, and finally we have to compute the actual offset of the line itself that we're going to be drawing. And you'll recognize this code as the code for multiplying by 80 that we've already seen before to compute the line offset. So that's all pretty straightforward. It gets a little bit more complicated from here. There's two cases that we have to deal with. The first case is this code here, and this is the case where both of the pixels are in the same byte. Now I'm not going to go through exactly how this works. It's just a bunch of bit twiddling to figure out what the byte should be, and then finally we write the byte to the screen. The more general case is the case where the endpoints of the line, the bytes that correspond to the end pixels, are not in the same byte. And so that's what this code here looks like. So you might notice that there's no, you can't see a loop here for drawing all of the pixels in between the endpoints. But it is actually there. So this is an instruction wrap in assembly language, which means to repeat this instruction, the storing, the part that actually draws a pixel, a certain number of times, and that number of times is stored in the CX register. So once we've drawn the first pixel, which is done here, we can just draw all of the other, or at least the first byte. Once we've drawn the first byte, we can draw all the other bytes with a single instruction SOSTB here with the rep prefix. So that'll just repeat CX times the drawing command. So that's going to draw all the pixels between the end bytes, and then all we have to do is draw the final end byte. So that's basically how this code works, and the rest of it is just bit twiddling to figure out exactly what the offsets are going to be for the endpoints, the pixels that we care about, the ones that we're going to change, and making sure that we preserve the pixels that we don't want to change at the endpoint. All the bytes in the middle of the line between the end bytes are all just going to be set to the same value, namely the color that we want. So each of the 2-bit fields in that byte is going to be set to the same 2 bits for the color, and we can just write those directly into screen memory. Well, we're going to overwrite whatever's there for those bytes. It's only the end bytes that we need to worry about what else might be there that we might be messing up. And so that's basically all there is to it. And this is very fast because almost all of the time is spent doing this extremely fast repeat of the write command for the middle of the line. So when you're filling the entire screen, you're just drawing horizontal lines right across the whole screen. It literally writes 1 byte for the first 4 pixels, then does a very fast output to the screen memory for all of the pixels in between, and then finally a slower write for the final byte for the line for the last 4 pixels, and then it returns. So this blanks the screen very quickly, or in fact sets any horizontal line to whatever color you set very quickly. That's all we have to cover really for this episode. So I hope you enjoyed this, and if you enjoy this style of content and would like to see more, then please don't forget to subscribe and like the video. If you have any questions or comments, put them in the comments section below. And don't forget to put the notifications on so that you get notified of the next video when we upload it. See ya!